Thank you, first of all, everyone, for coming along today. This is the first in a new initiative for the Australasian Wind Engineering Society. We're hoping to try and engage a bit more with the sort of practicing engineers and people from across different disciplines, not just engineering, architects, and, well, sorry, not just civil engineers, but architects, mechanical engineers, and so on. Anyone really interested in wind and wind's effect on people, wind's effect on structures. So for those, I know many of you are not actually associated with the Wind Engineering Society, but what we do is really try and look at research. Research primarily is what we started off doing, but now it's a lot in the consulting field as well, but looking at the interaction of the built environment and wind, and that could be structural dynamics of tall buildings, wind risk, wind hazard, wind vulnerability, all those sorts of things. So really what this lecture series is trying to do is trying to get out to the engineering and other communities what it is we do, and really trying to be a platform for interaction between engineering academics, engineering consultants, and all types of and design engineers and so on. So I didn't introduce myself. My name is Matthew Mason. I'm the chair of the Australasian Wind Engineering Society at the moment, and very happy today to have Professor Chris Letchford, which many of you I'm sure are aware of, who I'm sure he taught many of you at UQ many years back, and others that have dealt with him throughout his time with the Wind Engineering Society. So Chris is, well, just as an introduction to Chris is a Queensland boy through and through, but did his undergraduate degree here, went over to Oxford to do his PhD and worked for ARAP for a while over there. Then came back, taught at UQ for 10, 12 years, and then decided to move across the Pacific to the US, worked at Texas Tech for a while, and that's really where I got to know Chris personally. He was my graduate supervisor when I studied over there. He then came back to Australia at the University of Tasmania and has gone back to America. So he can't really stay still very long, so it was very good that we could keep him still long enough to give this lecture. But without any further ado, I think I'll let Chris take over and talk a bit about tall buildings, wind effects on tall buildings and their effect on urbanisation. Thank you.
Thank you very much, Matt. So this is a cut-down version of a talk that I gave at the 50th anniversary conference on wind engineering in Cambridge, England last year, and it's been modified for the audience a little bit, but I wanted to just give you the context of the talk so that we'll start on the same page. Before I do start, though, it's a real pleasure to be here. We have lots of family in southeast Queensland. We tend to come back once or twice a year to visit family, and I really appreciate such a great turnout on such a cold, bitter winter night in Queensland. You guys really struggle. I say that because my wife and I learned to ski this year because we had 3 months of sub-zero maxima where we currently live in upstate New York. And if anybody knows anything about upstate New York, it's really about the fall. October is the most spectacular time of the year to visit upstate New York, and so there's a standing invitation for any of you who need to come and see the beautiful colours of the fall of New England. October, and Rensselaer Polytechnic is in that region, or Albany, New York. Just a little bit about Rensselaer. It's the oldest civil engineering degree awarding school in the English-speaking world. The first degree was issued in 1835. The institute itself was founded in 1824. And was really to train surveyors for building the Erie Canal. And after that canal was completed, the engineers were trained then to build railways and bridges. And so amongst our alumni, George Washington Roebling of the Brooklyn Bridge fame, and a whole sequence of other bridges. In fact, all the bridges in New York City have an RPI connection. And another famous alumni of our program is George Ferris of the Ferris Wheel, which was designed for the 1893 World Exposition in Chicago. Now, my talk is about tall buildings, and I grew up in the 60s where in central Queensland we had TV for about 1 or 2 hours an afternoon, and in that time slot there was a television cartoon called The Jetsons. Is anybody familiar with the Jetsons cartoons? You're showing your ages, some of you. But the Jetsons was clearly a spin-off of the Flintstones, which was a much more popular cartoon program. But the Jetsons was clearly set in the future. In fact, it was set 100 years ahead, so in 2062. So those of you who've seen the Jetsons will be familiar that do you ever see the sky, do you ever see the land in the Jetsons? Anybody? Somebody up the back said that they'd seen the Jetsons. Do you ever see the planet Earth? And so in 2062, we never got to see the planet Earth. We always lived in the sky. And we lived in buildings that you'll see a bit later on in the show. So what else is 50 last year was a couple of things that I'm just pointing out to people. The smiley face was invented in 1963. And it was invented by an insurance company person who was clearly bored in Connecticut. The mouse, the computer mouse, was invented in 1963. Doctor Who began life in 1963. Clearly some major things were going on in the 60s. The Beatles had their first tour of Australia in 1964, so we're celebrating 50 years of that. But they released this album, Please Please Me, in 1963. James Bond was doing things with Russia in 1963, and he's still doing things perhaps with other villains these days. And of course, Bob Dylan released Blowing in the Wind in 1963. So the context of my lecture last year was about wind engineering and how it's changed in that time. And two of the most famous statements in 1963 were from President John Fitzgerald Kennedy, who went to Berlin and reiterated the importance of West Berlin in the divided Germany. And of course, Martin Luther King gave the I Have a Dream speech at the Lincoln Memorial in 1963. So that's the context of my talk about wind engineering at 50. If we look at buildings over that 50-year period, the tallest needle-type structure in the world 50 years ago was the Seattle Space Needle, which was built for the World Fair of 1962 in Seattle, 184 metres. If we look at the tallest needle-type structure now, it's the Sky Tree in Tokyo, and you can see that there's been a significant increase in height. Now, almost a factor of 3, or a bit over a factor of 3 in height of those types of structures. In 2013, we had our America's Conference on Wind Engineering in Seattle. 50 years of tall buildings. The tallest building in the world 50 years ago, or thereabouts, was the Empire State Building. It had been the tallest building since 1931 at 381 metres. And it would remain the tallest building in 1963 until 1972, when the World Trade Centers, and shortly after that the Sears Tower, that became the Willis Tower in Chicago, superseded it. And it was, of course, the tallest building in New York until World Trade Center 1 was completed last year. So it's had a remarkable career as a tall building. Clearly the tallest building in the world is currently Burj Khalifa in Dubai, at something like 830 metres high. And again, you can see a doubling in height of tall buildings in that 50-year period. But what was 2062 supposed to look like? Well, this is what the Jetsons' view of 2062 was going to be. Everything was on pods in the sky, very tall, slender structures. And of course, we're almost halfway there, clearly, to 2062, and I don't see any of those types of structures just yet. If you go to any, some of you will be parents, or some of you will be parents of sons, some of you will be parents of sons who play video games. Some of those video games will be set in the future. If you look at these pictures, they are all of cities or developments like this. Okay, that's one version of a future city. Here's another version of a future city, and here's yet another version of a future city. And they all have something in common, which I'm sure you wouldn't take long to work out. Okay, we're ignoring, of course, that coal fusion now powers everything and all transport is aerial. But clearly the buildings are all tall and slender. And how are we going to get to, if that's the future of futurists of the city, tall, slender buildings, and I've got that from a cartoon version, I've got that from a computer science game version, and a whole lot of movie versions, how are we going to get to, or why are we going to get to, tall, slender buildings? Okay, so really that's what this talk is about. It's about getting tall, slender buildings to work structurally under the loadings that we'll typically have to worry about. And from my point of view, that's only going to be wind. I'm not going to address earthquake loading. This is about wind loads on tall, slender structures. I've introduced the topic in a sense. It's about urbanisation. Why do we need tall, slender buildings? And how are we going to achieve those to resist the wind loads that they will be subjected to? Matt's already given the introduction. I've been at Rensselaer now for 3.5 years. And my wife insists that this will be our last move. So I intend to retire at Rensselaer Polytechnic, and they'll be carrying me out of my office in a box, I think. So in terms of the structure of the talk, I want to talk a little bit about urbanisation, the demand for tall, slender buildings. And I've been away from Brisbane since 1999. The city is almost unrecognisable in that 15-year period. From my point of view, the profile of the city is unrecognisable, the transportation network is unrecognisable and quite confusing for a recent arrival. I want to talk about slender buildings and the problems that slender buildings particularly have, and we'll talk about the crosswind response of those. So we'll talk not only, or not very much, about the along wind response, the wind blowing on the building and it moving in the direction of the wind. We'll be talking more about the crosswind response, the sideways response of the building. And then I want to talk about some of the applications that have been used for crosswind response, or mitigating crosswind response to buildings. And then hopefully you'll get a take home. So in terms of urbanisation, we are, or have just passed, 50% of the world's population living in urban environments. And in the next 25, 30, 40 years, by 2050, there should be about another 2 billion more people living on the planet. Most of those, or all of those, will be in urban environments, partly from an employment perspective and partly from a way of handling, the best handling of resources in that environment. So there's a huge population growth that's going to occur in the next 30 to 40 years. All going to be in urban environments. And really we have two choices with urban environments. We can spread out flat for a long way, or we can grow high and relatively slender in a more dense environment. Now, there are clearly reasons why you'd have one over the other. The first picture at the top of the page is of Mexico City, and they have a peculiar problem of earthquakes, and so tall, slender buildings don't particularly work well on the soup bowl that is Mexico City. The bottom picture is of Shanghai, I think, and it's a very dense urban environment where the choice has been to grow vertically rather than laterally. And my argument to you tonight will be really to say that the lower picture, the verticalisation, if you like, of accommodation is a much more efficient, affordable way of dealing with urbanisation than a lateral spread. And if we look at tall, slender buildings, there are really, or if we look at tall buildings at least, we can think about tall, slender buildings, such as this building, World Trade Center 1 in New York, on the site of the original World Trade Center buildings. Or we can also think of other types of tall buildings which are not so slender. Okay, and the advantage of one over the other. Now, of course, there is some family resemblance between these two types of structures, and they are the sort of structures clearly that resist lateral loads quite well, some sort of triangulation of the load. If we look about slender buildings, and that's the peculiar problem I'm going to deal with now because of the, really, we need to be developing within inner cities smaller and smaller plot sizes in a sense because of the value of the land in those cities. We are going to be looking at much more slender buildings. And here's a couple of examples, one in Melbourne, with a 10:1 aspect ratio, and another building in New York that's a 12:1 aspect ratio. These look quite slender. I didn't get a sense of the slenderness ratio of your two tall, slender buildings. Does anybody know what the slenderness ratio?
The one in Adelaide is 13:1.
13:1, and the one down on North Quay?
Bigger, a bit less.
Okay, so similar sort of aspect ratios to there. Does anybody have a sense of what the World Trade Center building aspect ratios were? The ones that got hit by the aeroplanes. Anybody got a sense of what their aspect ratio was? They were regarded as relatively tall, slender buildings. They were 8:1. Okay, so you have a picture in your mind of the World Trade Center buildings, 1,400 feet high, 200 feet, or actually 7:1, 200 feet square footprint, so 7:1. These are buildings that are pushing that at 50% increase in the slenderness ratio. The record for the slenderness ratio at the moment is a building in Hong Kong, Highcliffe, with a 20:1 aspect ratio, incredibly slender, particularly for a hurricane or typhoon region. And Sky House in New York City, currently at 17:1. If you look at the history of these sorts of buildings, though, we're talking about new buildings in New York that are going to be much more slender. They may not be as tall as existing buildings in New York City. You can see there in relation to the Empire State Building, 3 new buildings around the world, 2 of them in New York, where there are much more slender sorts of buildings going ahead. And only yesterday I was sent a picture from Central Park, or a montage of what Central Park will look like in New York in 2020, and you can see aspect ratios there of 23:1, 111 West 57th Street, the tall, slender one right in the middle of the picture there, 23:1 aspect ratio. Very small plot size, because the land is so incredibly valuable in that part of New York City that engineers are now being really challenged to make buildings of that sort of slenderness ratio work. And the question will be, why can't this be done all over the world? Well, clearly I've already indicated it's not a great idea in earthquake regions to do this sort of thing, and probably not a great idea to do it in very high typhoon or hurricane or cyclone regions, but in many other parts of the world not afflicted by those 2 areas, or those 2 natural hazards, tall, slender buildings are going to be very valuable ways of accommodating the future urbanisation of people. Now, why does it matter whether it's slender or not? This is a figure of a response, so that can be a long wind, crosswind. It's actually crosswind response versus frequency. So we all have done the ruler and flicked it and got a natural frequency of vibration. The same sort of thing with a tall building in the wind. If I flick it, I'll get a bigger response if I load it at the natural frequency. Some of you are divers. You will have stood on the end of a diving board and found its natural frequency. You jump up and down on that frequency, you'll get a much bigger response. And so that's what this is telling us. If I have a natural frequency here of 2, whatever that is, 2, well, it's 5-second period, so it'd be 1 over that, 0.2 hertz. I might have some response. If I have a lower frequency, a longer period, I would have a much higher response at that frequency because of the nature of wind loading. And so as we move from more traditional, heavier construction of higher periods or higher natural frequencies down to lower natural frequencies, we'll get much bigger response. And so this idea of looking at slender, tall buildings is going to be a problem for engineers in terms of the response of the structure under loading. And if we look at crosswind as the particular response that causes most problems, the long wind buffeting of a structure, just the turbulent, gusty nature of the wind causing the building to have a drag-type response, that's not as significant as the crosswind response, the lateral response of a structure. And there are many different ways of causing that crosswind response. And I'm going to be typically talking about this part in the middle, wake excitation. So where the flow behind the structure is causing the problem. And again, the figure really to talk about response versus frequency. If I excite it at a particular frequency, then I'm likely to get resonance. Resonance is one of those great opportunities to get something for nothing. Okay? If you use the resonant frequency for excitation, you can put in a very limited amount of energy and get a huge response out. So resonance is great if you're trying to generate something from nothing, but it's terrible if you're trying to avoid it. Okay? So resonance is when I'm going to load it at the natural frequency of the structure by the fluctuating wind or indeed the fluctuating flow behind the structure. So I want to talk about two ways that we can improve the performance of tall buildings under crosswind response. So I can talk about changing the shape of the building or changing the stiffness of the building, and I'm going to refer that as solidic or solid aerodynamic modification, and I'll change the shape or the stiffness of the damping. I'm changing the geometry of the flow. And fluid aerodynamic damping is something, or aerodynamic modification, sorry, is something where I modify the flow specifically. I don't change the structure, I don't change the stiffness, but I change the flow in a manner to improve the performance of the building under crosswind loading. And that's something that's very commonly used in aeronautical engineering to control flow over an aerofoil. And we're, in a sense, modifying that sort of behaviour for aircraft to the built environment to look at how that might play out in buildings. So I want to just talk to you a little bit about these two ways that I can improve the performance under crosswind loading for tall, slender structures. If we look at SAM, that's solid aerodynamic modification, and I'm sure you can see examples of this around even Brisbane when looking at your high-rise. There's a whole range of ways of playing with the shape to improve the aerodynamic performance. The clearest example of that is probably changing with the profile, so stepping the profile or tapering the profile, or indeed changing the plan form, changing where the flow separates from the structure. So you can see a whole range of different plan shapes and profile shapes that are being used by wind engineers and structural engineers to improve the crosswind response, the sideways response of the structure. And I'll show a couple of examples of that later on. Maybe it'll go ahead. Here we go. So if we look at plan form of structures, the World Trade Centers were square, the Willis, and square all the way up. So they were 7-to-1 rectangular cylinders, tubes. The Willis Trade Center or the Sears Tower is also square, but had a bundled tube arrangement where the tubes terminated at various levels. So you changed the profile of the structure. And that interfered with the flow around the structure in a manner that was helpful to avoid crosswind response. Type A101 has this sort of pagoda-type shape, so again playing with the profile. And Burj Khalifa is again a triangular structure, or but also tapered, so it changes profile vertically all the way up. If I look at fluidic aerodynamic modification, and that's changing the flow, so how am I going to change the flow around a structure to improve its aerodynamic performance? And the way to do that is clearly to inject flow somehow. So you can see here various ways of, if I inject flow, I change the flow around the structure, and by doing that I change the pressures, and I also change now the loadings on the structures. And some of you will have played cricket and you will have spun a ball. That is not unlike injecting fluid to the side of a structure, and you're creating now a lateral force, and of course in a cricket ball that causes it to curve. So by a Magnus type effect, I'm changing the flow. There I'm spinning the ball. If I could inject flow behind the structure, then I can change the flow around the structure and hence its aerodynamic performance. Now, of course, we don't want wobbly structures because people won't accept wobbly structures. You as structural engineers are interested in designing buildings for habitation, and that generally means people need to be able to carry out their tasks without interruption. So wobbly buildings are not required. These are, of course, real wobbly buildings. One's the left-hand side, Ginger Rogers and Fred Astaire. They're two buildings in Mississauga and Toronto. where the profile's been warped up the building to change the performance, and the other building is somewhere in Germany, I think, but I just wanted examples. Now, why don't we want wobbly buildings? Because buildings that move around cause people to be uncomfortable in wobbly buildings. And what you're designing for is a response of a structure to a certain level of vibration, of motion. And there are various ways of doing that. Typically, we look at acceleration of a floor of the building against a frequency, and there's a whole range of different criteria that are now used to design a tall building. A tall building should, in my view, never fall over under wind loading, but it may well move around too much. And if it moves around too much, then people probably won't be happy renting that floor space. So we're interested in controlling the amount of motion in a building under this lateral loading. And why do we get this lateral loading? Well, again, it's a fundamental phenomenon in fluid mechanics that if I have a flow and a linear two-dimensional sort of structure, then as the flow takes place around that, I will generate separation from that, and under certain circumstances I can get now a street of vortices. And those of you who live anywhere near the Brisbane River will have looked at bridge piers. You will have seen dimples of water floating alternately down behind the bridge piers. That's vortex shedding. That occurs at a fundamental frequency, the vortex shedding frequency. And that, if it becomes the same frequency or the natural frequency of the structure, we generate the opportunity for resonance. That the flow will cause an alternating flow pattern, okay, at the same frequency as the structure, and that will generate resonance. We don't have to put in very much energy to get a big response out of the structure. And that's to be avoided if you're trying to avoid accelerations at tall buildings. So here's some examples of flow simulations around relatively tall, slender structures. You can see sheets of vortices forming. Clearly near the top there's something special going on as the flow goes over the top. But clearly we can generate, at least for long two-dimensional structures, this street of vortices behind it, the von Karman vortex street. And that alternating flow pattern leads to alternating pressures, which leads to ultimately an alternating crosswindy force. And that's the one we're trying to avoid. And the peak of that is typically the Struhl number or the frequency of vortex shedding. And we need to avoid that if we're going to eliminate motion. So a lot of my wind tunnel colleagues have spent a lot of time looking at a whole range of different ways. Here's just cylinders, because if you think of tall, slender cylinders, the classic example are chimneys. And I didn't bring it along tonight because I wasn't sure about videos, but there's a very nice video of a couple of towers from a power station in Sydney that Barry Vickery took, of vortex shedding from one chimney interacting with other chimneys. And so you have the 6 chimneys vibrating substantially in and out of phase. And so a lot of work's been done on chimneys, and I'm sure many of you have seen some of the examples of that work. They might be helical strakes to disturb the flow around the top, create more three-dimensionality of the flow. There might be porous shrouds, a whole range of different ways of treating the response. And so you, again, see this idea of a graph of response versus frequency, and I go from a peak under a certain type of resonant condition. I drop that down completely by creating this spiral effect. This has come to a fore again with long-span bridges, particularly cable-stayed bridges, where the frequencies are quite low, and you get the opportunity for rain-induced vibration as well on these sort of long-span cylindrical structures for certain wind conditions. So there's a lot of work being done in this space in modifying the structure. Here we're changing the shape of the structure to improve the performance, to lower the response at the resonant frequency. And of course there's a whole lot of new buildings where that's been taken into effect as well. The building on the left is in Qatar, I think, it's now completed. The building in the middle is in Malmö, Sweden. These turning torsos or twisting buildings are again great ways of disturbing the flow. They act, if you like, of giant helix strakes on chimneys to disturb the flow to improve the performance. And then there are other ways of disrupting the flow. You saw shrouds or porous shrouds, and you can make very rough looking buildings, and I certainly noticed the building down here in North Quay. I don't know what it is, but it has very large blades. Maybe they're to do with the sun as well. But that would certainly be a way of disrupting the flow on a very tall, slender structure. And this is a new Frank Gehry building in New York City, where he's taken on the cladding in a way to try and improve the aerodynamic performance. So another classic way of dealing with this crosswind response is to change the shape of the structure, and cutting corners is a classic way of doing that. And here again you'll see examples of a reduced response, so we're not getting the same amount of motion, if you like, by changing the corner chamfer. And this has been put into practice over a long period of time. Those of you familiar with Melbourne, the NAB building, Bill Melbourne did this tunnel test, and again, slotted corners on this building improve the aerodynamic performance of the structure. And of course, this application Bill took to a whole new extent with sports stadia, where he introduced the slotted edge of the sports stadia to again do this same thing of interfering with the flow as it separates, so to try and make sure that any sort of wake excitation is eliminated. So again, it's a way of fooling the flow so that it doesn't cause this resonant type condition to occur. And again, changing the profile is clearly another way of doing that. It's the long, slender structure in a more or less uniform flow that has a problem. In the part of the world that Matt Mason and I worked for a long time in Texas, we had very wide streets, because everything is bigger in Texas, and we had very long traffic signal arms, because there were 5 lanes of traffic going nowhere, but they still had to go somewhere. And these long-span traffic signal structures would spend all day just going up and down, vibrating at their natural frequency, about 1 hertz. And it would be hardly any wind would cause these things to move more than a diameter. And we're talking about 70 feet, 20-something metres, okay, expand. So they'd spend all day. And of course that motion at 1 hertz for several years generated a lot of fatigue failure. So changing the profile is really important because it destroys this vortex shedding flow. And of course you've seen that in Burj Khalifa. But if you've been to London recently, the Shard on South Southwark is another building that's using the profile to change, to improve its aerodynamic performance. Are there any Arabs in the audience? Europeans? Okay, well, apologies to you guys. This is the Millennium Bridge, which had a few problems when it was first opened because it had lack of damping.
It wasn't wind though.
No, it wasn't wind, it was people-induced, and I'm quite aware of that. But it had a problem with a lack of damping, and so the Shard doesn't need damping because of its profile. And again, a whole lot of ways of changing the profile. I have colleagues and this information is available on the internet. If you go to Tokyo Polytechnic University, they have a fabulous facility for you to check the aerodynamic performance of a particular shape of a building. They've got all this data in a database, a very easy to use, if you like, interface to look at the crosswind response of a structure for various shapes, and they've done all of these different types. And again, you can see clearly, again, a reduction. The response is the vertical axis and the horizontal axis is basically frequency. You can see that these sorts of things playing with the shape, the profile of the structure, reduces the response. So that opportunity for resonance disappears, and we can now have a much less severe condition for our structural response, our human perception of motion response, by changing the shape of the structure. And here you can see the rectangular or the square rectangular shape, the black line, giving this really large response at the resonant frequency or the Struhl number. By tapering, by twisting, by stepping, by cutting the corners, you can generate more or less the same amount of reduction in response. Okay, so you can change the response quite dramatically in that sense, and this is an order of magnitude, so it's fairly important. Now, of course, another way of handling this problem is to increase the damping of the structure, and that's a fairly classical approach used by structural engineers and wind engineers. So there's a whole range of different technologies for using dampers in structures, just like we now have much better drives in our Ford Fiestas or Ford, whatever the Focus or whatever the Ford is here, instead of a Model T because of dampers. You'll get a much better ride in a tall building with a damper because, again, you're doing the same sort of thing. You'll have a reduction in the response because you're really increasing the energy dissipation in the structure by the use of dampers. And classic examples now include not only friction dampers but fluid dampers, tuned mass dampers, a whole range of dampers, which, again, there's lots of resources on the internet for that information. But all you're doing is extracting energy out of the flow. Instead of letting it going into the building, or you're letting it go into the building, but you're not letting it excite the structure, you're letting it excite the damper. And that'll improve the performance of the structure. Now, of course, everything I've really shown you has been isolated. We've talked about isolated tall buildings. And here's an example from a colleague of mine, Kenny Kwok, in Hong Kong, who did quite a lot of work on the interaction of just two buildings. And again, it's the same sort of phenomena that if you've been ever riding a bicycle and in the vicinity of a bus, you're quite aware of where you should and shouldn't ride because of various flow conditions. So it's the same idea here. If I have buildings upstream of my test building, so the building on the right is going to move around the screen, I'm going to respond, I'm going to measure the response of the building at the origin of the axes, then I can plot now the amplification, if you like, of now both a long wind and a crosswind. And there are certainly regions of the flow where I've got much larger response. Here's a 50% increase in response if I put my building here. Here's a 75% increase in response if I put my building directly upstream. Or 60% increase if I put it just downstream. So you can see that the relative locations of buildings is really very important. And this is just two buildings. Okay? Some people have done some of this work for 3 buildings, but it becomes almost impossible to look at all the parameters in this space with this sort of response. But it can lead to significant increase in response, just the interaction of buildings. Okay, so I want to switch gears now and I want to talk about fluid aerodynamic modification. So that's not changing the shape of the structure, not adding to the stiffness of the structure, not adding to the damping of the structure, but just changing the flow, manipulating the flow around the structure. And of course, all of the things about changing the shape or adding stiffness or adding damping all takes up internal volume or takes away internal volume of the structure. If I cut corners on the structure, then I'm going to lose rentable space. If I add dampers, if I add stiffness, more massive structure, then I'm taking away from rentable space. And so the opportunity to take away for that and still achieve the same volume of rentable space typically means I have to increase the height of the structure. And that's a classic way of chasing your tail. You're now going to a taller building that's going to be more slender effectively and have greater response. And so that becomes an impossible journey, a Don Quixote challenge. What we were looking at RPI with a couple of students of mine was to look at now how we could modify the flow by injecting flow around the building to improve the performance, particularly in crosswind. Now let's stand back and think about why would you inject flow? Why would you inject flow, or how could you do that? How could you inject flow into the structure, into the flow around it? Well, most of you work in office buildings, is this true? Does anybody not work in a... I started my working career in 45 Fortescue Street, Spring Hill. It was a timber house where we parked the cars underneath. Okay? But that's not where many of you work now. Most of you work in air-conditioned spaces, don't you? And typically you have an exchange of air between the internal and the external space, and typically that occurs at a number of levels. So air is drawn into the structure and air is exhausted from the structure. Our plan was to utilise, and is to utilise, the air exchange for air conditioning to improve the flow around a building. And so we did a whole range of model studies. Here's an example of our model. It's a 15:1 aspect ratio, 2:1 plan aspect ratio building, where we had the ability to inject flow at various levels on either side of the building. So it's a way now of not changing the shape of the building, not changing the stiffness of the building, not adding to the damping of the building, but to use the resources of air conditioning the building to improve the structural performance of the building under wind loading. And again, you can see here a plot of response versus frequency again, and you're seeing a change in the frequency as we move from a small injection of air. Red is no injection of air. This is only from one side of the building. We're injecting air at various speeds, okay, fairly high speeds in some cases, but you can see a change in the response of the building, both a reduction in the frequency and a reduction in the amplitude of the response. And some of that can be very significant in terms of the response of the structure under design conditions. This is really just a exploratory study that we undertook, and the way we're interpreting this is really the fluid is doing two things. It's sort of rounding, it's reducing the overall amplitude of the structure, of the response. So by injecting fluid, we're making it easier for the wind to go around the structure, if you like, and that allows the wind to see effectively a more aerodynamic profile. And the frequency is changing, and that's really saying that the wind is now seeing effectively a narrower building. So we're reducing the load. We reduce not only the crosswind response, but we also reduce the alongwind response, or the drag response, in this manner. And so the whole purpose of this project, which was joint between the School of Architecture at RPI and the School of Civil Engineering at RPI, was to look at facades and to look at boundaries between internal and external space, and to try and look at blurring those boundaries, to get away from the fact that this is a boundary between an internal space and an external space, but a boundary that could be manipulated to the advantage of everybody, so that we could manipulate the space at that interface for the improvement of the aerodynamic performance. So I'm nearly over. That should give us plenty of time for questions. I just want to recap. We've talked about urbanisation, and I think the need for taller, denser cities. And in the 15 years I've been away from Brisbane, that's certainly happened. You have a much taller, denser city, so you see it here in your own backyard. I've talked about slenderness of buildings, and that's because we're dealing with plot sizes that are relatively small in inner city spaces because of the cost. Talked about crosswind response. That's the sideways motion of the flow, and ways to control that, either through solidic aerodynamic modification or fluidic aerodynamic modification. And then I've given you some examples of that. In terms of the take-home, Alan Davenport is regarded as the founder of wind engineering. Alan Davenport was an Englishman, born in India, grew up in South Africa, led a very famous research group in Canada in wind engineering. And he, with Jack Cermak, really founded the field of wind engineering, more or less around the wind tunnel study that described the wind loads on the World Trade Center, so the first World Trade Center buildings. And in 1963, he was present at the first conference on wind, international conference on wind engineering, and his question with the amount of data that in 1963 was that question: how can we use all the data that we've collected up till 1963 in a codified way? Those of you who use wind load codes, if you've used them over time, they've got probably more complicated and more demanding. That's because there's a lot more data now. We will generate in the year to date, in 2014, we will generate more data than there was ever existing in up till 1963. Just in the first 6 months of this year, we'll have generated more data on everything than was existence in 1963. So Alan Davenport's question about how we're going to use all of this is even more valid today. We have much more data, and you have tools such as I've said to you about the Tokyo Polytechnic University database on tall building crosswind response, but it's still a big problem. Okay, and it's really what wind engineering is all about, addressing that problem of how we handle wind loads on structures, and particularly how we translate what the research has done in wind tunnel studies and in computational studies into codes of practice and the like. And I think that pretty much brings me to the end of my talk. I thank you very much for your attention, and I look forward to any questions. Thank you.
Thank you, Chris. We can't get the roving mic to work, so when people ask questions, Chris, if you could just repeat, that'd be good. So the floor is open.
Leighton Cochrane.
Your second group of... This will be a bit intimate. Your second description of FAM, there's two buildings in Hong Kong in the 400 metre plus range that have completely vacant open floors at quarter points up the building. And the motivation had to do with fire suppression and other things, but it had the net effect of reducing the wind loads on the buildings. Would you put that in the same category as your FAM, even though it's passive?
I think it's changing the shape, so it's solidic aerodynamic modification. You're changing the shape to create the performance. And there were examples of slots through buildings in some of the, the big charts of multiple types of plan forms. So that's still a solid aerodynamic modification. What we were looking at, particularly with the School of Architecture there, was to really see how we could use expelling air from the building in an efficient way. Could we use that? Because, the design criteria, a serviceability criteria maybe once a year or once every couple of years, could be managed by this expulsion of air quite well, probably. Okay? It doesn't have to happen all the time. It only has to happen on the design day. And, well, I think there was a question up here first.
Look, I've just noticed some research coming out of the States, I think, that suggests that the probability of getting a cyclone is moving closer to the pole, which means in the northern hemisphere it's moving north and the southern hemisphere it's moving south. And it's moving quite rapidly. I mean, it's not happening.
Hollywood sense.
Happening rapidly. Does that mean we should be thinking now about increasing our design wind speeds for Brisbane, or would that be jumping?
No, it's not moving that rapidly, in my view. So I don't think you need to... I've just had a PhD student who spent 3 years looking at the impact of tropical hurricanes on the northeast of the United States. I mean, we typically have, by the time they get to New York or northeast New England, there are more rain events than wind events, but Hurricane Irene caused a huge amount of damage in New York City, largely from storm surge and flooding, not so much from wind. There are a couple of construction cranes come down, but otherwise it wasn't really a wind event. My sense is, and from her work, there's the opportunity of maybe a 10% increase in wind speed by 2100. If we look at all the simulation work that we do for predicting hurricane impact on the east coast of the United States, if we look at importing various climate change RCPs, concentration pathways, if you like, climate change scenarios, we take the worst case, it's about a 10% increase in wind speed for New York and the northeast of the United States by 2100. Okay, and that's based on, the east coast of the United States, using only landfalling hurricanes, is a database that's fairly accurate for several hundred years. Certainly from 1850, they're very confident of having a good idea of landfalling hurricanes on the east coast of the United States. So we're dealing with 150 years of data, and looking at that work, this is the sort of work that Matt's done as well when he was with insurance industries in Risk Frontiers. Looking at that data, it's possible to make some sort of idea of that sort of increase by 2100. So that's not something that I'd be typically very worried about.
Do you think George Jetson would have a reliable CFD tool for designing his buildings in 2062?
Everybody hear that? George Jetson. I don't think George had much of an idea about work from my memory of the cartoons. It was managing the family that was his big struggle. CFD is very powerful. I get very concerned. I had an architecture student who became extremely proficient in CFD after about 3 months. It just really worried me because I've just had a PhD student who spent 3 years in engineering trying to work it out. So, you know, I think Leighton has had a wonderful presentation on this topic at a conference in the US. So he's the expert, in a sense, to talk about the role of CFD. It's in my academic career of nearly 30 years, we've been talking about CFD taking over from physical modelling, and it hasn't happened yet. And I'm pretty sure I'll be able to finish my academic career still with a lot of, if you like, information and data sourced from the wind tunnel as opposed to the CFD. So we're getting much more powerful, much faster computers, but the ability to simulate turbulence in a meaningful way in these very complex flow patterns of inner cities is getting better for climatology studies, so wind environment studies, mean flow patterns, but turbulence and looking at extreme pressures and that sort of thing is still a long way off in my view.
2062?
2062, I'll be 103. I'll be hanging out for the day when I get on and play with my computer and CFD. I mean, my children have iPads, of course, as all children have these days, and you can buy a flow one, and you can draw shapes and let the flow go around it. So we can be experts now in flow around 2D structures, at least according to the iPad. But you know, I mean, no, I think there will be greater use of these tools. There's no doubt about it. They still are, in the hands of amateurs, extremely dangerous. Okay, they're extremely dangerous in the hands of amateurs. Yes.
I'm just curious whether in your study that the volume of airflow that you get typically from air conditioning units was sufficient to have a significant enough impact, or if you then looked beyond what happened if you increased the airflow. So in other words, if this were to become a reality, how much are you looking at modifying the traditional mechanical systems in buildings we use at the moment?
That's a very good question, and the work was sponsored by SOM in New York, and so their office was involved in estimating the flow, and it was really about creating more distributed systems, so each floor would have their own air handling unit, in a sense, and so there would be injections at each floor, or maybe, you know, not the usual sort of 10 floors of services concentrated in a service level, but much more distributed. And they didn't feel that there was a problem in terms of generating the sort of flow that we needed to modify the flow in these circumstances. But it's still very early days, in a sense, in this work. And the work that I'm doing here is with CASE, the Centre for Architecture, Science and Ecology, and their work is really about a holistic approach to tall building design. So not only looking at indoor and external air, but indoor and lighting, shading, energy flow in and out of the facade. And so it's a part of the integrated package of improving the interface between the external and the internal. And this was just one aspect of it where we, you know, did have air that was being exhausted. Could we do that in a more efficient and effective way for looking at aerodynamic response? And we certainly demonstrated that it's possible to change the flow with the volumes of air that we needed. Okay. May not be enough in the design case, but that can be modified down the track.
Question, just with the flow that you're putting around the building or outside of the building, whatever it was, is that something that's just constant, or was that being varied?
So the study there you have is constant flow, but we're about to go to the wind tunnel when I go back on Saturday. Next week we'll be in the wind tunnel looking at pulse flow. So I'll be looking at pulse flow because, again, what we're trying to do is put in as little energy as required to get a maximum response. So we're actually going to use resonance in our favour this time. We're going to be pulsing the flow at such a frequency that it causes resonance of the separating flow, and so it reattaches. So we're going to use resonance. So that's the problem with the airflow here. You know, if it's constant, that's what you saw, the results for constant airflow. So it will vary a little bit with wind speed, but I'm looking at the design case. So I'm looking at the 1 year response for acceleration of the building. So what's the 1 year return period wind that causes the response that I'm after to design for? I'm going to inject flow at that speed, and it's a ratio of the injection speed to the wind speed that's important, the blowing ratio effectively. It's a non-dimensional parameter. But it's a good question, and what we're going to do is pulse the flow, and this is what they do in Boeing will be trialling on the vertical stabiliser, the tailplane of their new 787s, synthetic jets. So these are little flat discs with slits in them. They have a piezoelectric diaphragm that can be pulsed, and so you inject air. There's hardly any actual flow movement because it's just going in and out of a little like a speaker, if you like, air going backwards and forwards through a little slit. They're going to try this on their aerofoil to give them much better response for keeping the flow attached to the tailplane in a synthetic jet inside. So there's very little energy required. Of course, aircraft, they can't have masses of energy tied up in controlling the flow. So they want to do this with these piezoelectric synthetic jets. And it's very common now in aerofoil flow control to use synthetic jets, where there's no actual mass momentum exchange really. The flow is just slightly pulsed in and out. You're using resonance to trip the flow in the right manner to keep it attached. And that's what we want to do here. We want to use resonance to our advantage now to cause the flow to reattach and disrupt the vortex jetting. Yes?
You mentioned that buildings are getting taller. Do you think that tall buildings should take advantage of wind power generation?
So the question's about wind power generation from tall buildings. There's several examples of wind power generation from tall buildings trialled. There's Guangzhou has a building, SOM design, with flow through at 1/3 and 2/3 heights. Some of you may have seen it. Profiled. It has 2 vertical axis turbines, one behind the other. There was a presentation given on this at the Boston ASCE Structures Congress. The question about has it met design specs and energy generation was quietly battered away. There's a building in London that has 3 Mercedes-Benz profiles in the roof, in the tapered roof. They've never been known to turn. Wind generation, to me, should never be associated with buildings. There's a building in Hobart. When I was at the University of Tasmania, the harbour office at Hobart had 4 vertical axis turbines on the roof. One of them decided to shed some of its blades one day, and that in the middle of the city wasn't such a good idea. The air is far too turbulent around a tall building. Tall buildings, unless they're airport control towers, are buried in typically roughness. They stick well above in some locations, but they're buried in roughness. Turbulence is the enemy of wind generation. You know, you want wind energy generated in very smooth flow without turbulence. You know, we're lucky that aeroplanes generally fly in smooth air. If they flew in very turbulent air, then more wings would fall off, and that wouldn't be good for air transport. But I personally don't see any future in wind energy with buildings. I just don't see it as a viable way. It's very attractive for developers, but it's not very effective. Now, Leighton might have a counter-response.
No, actually, I just wanted to agree with you. I've been involved with 3 buildings. Oh, here we go again. I've been involved with 3 buildings that had those designs, and none of them had better than a 30-year return for the investment, which is not very good. And one of them in Houston lasted for 6 months, and 2 of the vertical axis turbines flew off and landed in a park and caused damage to 2 cars. Again, because of fatigue, like you were talking about. And that's on the internet. You can look at YouTube, you look at Discovery Tower, Houston, turbine failure. Someone was in the park with a video camera, that's all on film. And you can't insure them.
So I think they're mobiles. They're not really for effective generation of energy. There was a big push in New York after Hurricane Irene, of course. Lower Manhattan flooded, and that had substations for most of the towers in Lower Manhattan. And I have colleagues in Lower Manhattan that were out power for over a week So they, couldn't use lifts, they couldn't have any, they basically had to evacuate. And so there was some thought about could have incorporated some local generation, but it's so ineffective. It's so ineffective. Yes?
Intrigued about the effects and the peaks associated with your upstream and downstream additional buildings.
Yes.
Second building.
Yeah.
What I suppose flags some concern to me is that if we look at Brisbane, with a number of large high-rise mooted for the very near future, while we're all very excited about testing our tall buildings in wind tunnels, what we're not doing is actually checking what the effect is on downstream or upstream buildings, particularly when you could be talking of 4 to 5D, which in this case is potentially in the vicinity of 1.5 kilometres.
Mm.
Is there any thought about what we should be doing about this? In that I'm assuming that developers aren't going simply to be paying out tens of thousands of dollars to be retesting their buildings because someone's building a building 1.2 kilometres upstream.
Well, I am aware that the question's about how do you plan for the future with development of tall buildings. And I'm aware that some buildings have been wind tunnel tested, particularly if they're doing recladding of the building because of adjacent buildings. I am aware when I was working at the University of Queensland with wind tunnel tests, and I am aware Leighton can speak more to this with his work with CPP and consultants, but I know that wind tunnel consultants typically look at what developments are likely to go ahead in the environment and have a quick placement of a building. It's not difficult to run a wind tunnel study for the base balance crosswind response for an adjacent building that's on the plans. So it's not uncommon for wind tunnel people to do that. Usually we're talking about buildings that are bigger than the ones that are already there, and so you're generally sheltering the building. We saw 2 buildings of the same height and the same plan form, and that was the interaction you saw. But in an inner city environment where there's a whole cascade of building heights, the effect of one on the other is less so. Now that's not quite the case here in Brisbane because you've got the river and then the other side of the river is not typically developed. So I know when I was here that Riverside Place and some of those buildings along that reach of the river had a very, very strong free stream exposure upstream to then buildings adjacent to them. And so there were studies done on some of those buildings, looking at other buildings around them. But by and large, most cities develop with a cascade of buildings, and it's fairly rare that you have a totally isolated high-rise building. Now, there's some examples of that in Chicago on the lakefront. There's a couple of very tall isolated buildings, and so there would be a case where you'd want to very carefully look at an old building if you were putting a new building nearby. Did you want to comment on that at all?
No, I can talk later if he's interested.
Okay. Yes?
You mentioned you're looking at using pulse wind streams to use resonance in your favour. Have you got an idea of what type of magnitude reduction you might achieve from that?
Well, you saw about a 5%, maybe 10%, if we're lucky, reduction in the amplitude, but it was the frequency change that was more important because that takes us out of, that changes the wind speed dramatically, and so that changes the return period that I have to worry about. So even though the reduction in amplitude was fairly small with the continuous jet, with the pulse jet, we actually anticipate much better response, and the PhD student who'll be defending next week for me has done a whole lot of computational work. We've done some calibration of this computational work, 2D and 3D. I've yet to see the results in turbulent flow. It's been more or less uniform free stream flow. But there he's seen 40% reduction in crosswind response, the RMS, by pulsing the jet, by using resonance. And that frequency is about 10 times the vortex shedding frequency. So the big vortices that are being shed, if we excite that at about 10 times that frequency, we don't need a lot of flow, we just excite it at that frequency. We're going to use resonance, and it's worked effectively both in reducing the drag, the along-wind response, and the crosswind response by between 20 and 40%. So that's fairly significant. We hadn't tested those in the wind tunnel because our it's quite difficult to generate the pulse flow uniformly over the structure. So we're going into the tunnel next week to do that in Canada.
All right, I think we'll bring it to a close, and we're already 10 minutes over. Just like to thank Chris for coming along and giving the talk. Hopefully we'll have more of these lectures put on by the Wind Engineering Society, so please keep an eye on the website. And for those that are not members, please consider becoming members of the Wind Engineering Society, and you'll automatically be kept up to date with when the next one will be. So just everyone put their hands together for Chris, and thank you for coming along.